So, everybody's here? Good. So we continue with the sustainable class. Sustainable, not design, don't be confused. And you just complete an assignment that was a proposal for a process to recover elements from waste. That was the whole topic. Recovery. It was specifically germanium from flue dust. And that wasn't mean a proposal. Straightforward, a proposal. It's something that you're proposing to do. And you end up with a feasibility study. I mean, you give me a lot of information, paper, reference. You work 3-4 times more, but this is part of the exercise. You give me a complete document. So if I work 2 more weeks, I will end up with more literature review, with a mass balance, okay? So the one that you give me, it's a pre-feasibility study when you have data, okay. A proposal, it's telling you have this, of course you need to review information. Of course you need to review. So you say, according to these 2-3 references, there is a content of from 0.2 to 10 ppm, depending on the origin of the flue, or the flue material. That requires to be characterized chemically, not literature. Okay? You say, okay, it's possible. If I say something, okay, we want to extract uranium, okay, we didn't find any reference showing that there is uranium. For example, understand? Understand the difference? And then there are alternative technological processes. You can mention them. And show a couple of examples. So, in this feasibility, first of all, it's the characterization. You have it. You have the characterization, then the possible processes in order to recover. And that requires to get kinetic data. For example, we have this type of kinetic data that can be done in a lab scale. You need to demonstrate that it's possible. It's possible to do because there are examples. You have this material, but you don't need to show everything. You need to keep it for a report. So this is an example. A more alternative can be found, but you already have 10 alternatives. You know what I'm trying to say? You already have, because you review a lot of papers, and perhaps you already know, you already learned, you already understood, but this knowledge is for you. Okay, you just show that it's possible. Okay, and then you can say, hello, hola Francisco. Joining. Hola Francisco. And then it's very important to demonstrate. Those are material that you are taking from papers, books, it's references. Okay. But now you need to show that you have a capability as a group, as a person, to produce something new. And you can say, however, for example, since you're working with fine particles, a new process must be designed. And the conceptual design, block diagram, is something like that. You already have it. Remember this key point. Always, pre-feasibility has references. They can be tracked. Here, to some extent, you give some, but not all of them, because we just complete. Francisco, ¿puede escuchar? Can you hear?
Sí, profesor.
Very good. So, we did a proposal. I can show you, you can translate it in Spanish. A proposal for a big project, $10 million project to replace smelter. We just applied with my colleague Fernando, who works in out-to-date reactor. So the people who was doing the proposal was asking us, give us reference, give us mass balance, give us information. So, because they can take this information and create a term of reference for a project. So we risk. So it was kind of weird that we're asking too many references. Okay, you can say we found 10 to do more references, but you don't say more because it happens. It's not fair, and it's not because of Chile. It happened also with Eramet, the French company. My colleague Aldonza, who is the head of the technology transfer office, she present in France to the research center how the technology transfer is done. Okay, methodology, stuff like that, in order to have a consultancy and receive money for that. Thank you very much, and that's it. And they hire a French company. That happens very often. Okay? So again, reference can be tracked, demonstrated, solve the problem. Okay, you say it can be done. There are other processes similar that have this following process. It's feasible to do it. Very important point here. Your proposal, unique, innovative. You need to tell that it's new, it's difficult to do. It's showing that they need to hire you. Check that. And this is, okay, fine particles, it's difficult for scaling up because of rheology. You can talk about that because it's well known. So that will impact the size of the equipment. So if the fine particles, we want to mix fine particles 10 micron, it means, what it means in practical terms in an agitator reactor. What it means. When we're talking about fine particle, we have a solid liquid conductor. What it means in practical terms of the operating conditions of this fission reactor, and how does impact the economical evaluation.
When you're working with agitation and fine particles.
And
fine particles, they're using with the shear.
Yes, so the limiting factor will be in an operating condition. More than this, yes, it's mixing. But as a consequence, as a flow rate, you need to work with more dilute pulp. Less solid content. You know that, all of you know that. And you can tell. That means I follow the sequence. The less solid content, it can be, for example, 10% solid. Don't mention volume here, don't be that technical. Because we know we need to work with volume, because the cost is related with volume. 10%, that impacts, what impacts if you have 10% solid? You need to put a lot of water and solid, solution and solid. You have a larger reactor. That will impact the capex of the project. You mentioned. Because you need to sound clever. Not only, okay, the thing that you shouldn't do, because it also happened to me, we are not talking about the kinetic T to the N, kinetic with Klimper model. At this level, in this proposal, we don't talk about that. We mentioned that also kinetic is also difficult. It's not the case, but it can be with distributed constants, such as blah, 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 blah. You need to demonstrate that the problem is complex, but you're not giving the solution. That's the same one I'm trying to say. It happened for one of my colleague. We are applying for a big budget for leaching. It was leaching, and we went with the kinetic curves, showing that if we do it in that way, you will reduce. You will have a smaller equipment. And the guy who was giving the fundings, they said, we don't care the technical part because we know that you know. We want to know your business model. So that was our mistake because we didn't have enough information of the final client. Okay, to make this thing short, you need technique and then propose what are the steps. The step is characterization for, what are the real steps for that? To do this project in a readiness level 4. Readiness level 4 means it can be bench scale but using real material. What are the stages that we need? Stages. First, characterize. So it means X-ray diffraction to know what type, or Quemscan in order to know the minerals, then chemical assay in order to know the elements, particle size distribution, analyze the variance of different samples. You have a variability because you have different samples. It's characterized, isn't it? Total expert characterization. That will be enough as an experiment because we will charge for that. Okay? And then we need to we already proposed the block diagram process, some of the equipment proposed as a block diagram. You don't mention equipments. Okay? Block diagrams.
You just mentioned the process, so what should we?
You can mention also you can say a box that says solid liquid extraction, leaching. You can say ionic extraction, but it can be ionic exchange or solvent extraction. Okay? So carefully, it happens. I'm an old person. It happened many times. Many times. And I can show you what we did this year with the proposal. Because the guy were asking, more reference, because I can take this whole proposal to someone else with the knowledge of autoclave reactor, which is few people. But all the secrets for the industrial scale, they don't have it. But we keep that. Well, to finish that, and then experiment. Experiment, you talk about bench scale. It can be 100 cc, 200 cc. You have leaching test in low concentration of solids because you want to avoid any mixing effect. This is kind of standard, okay? How to do that. We will come back to what type of experiment and how you're scaling up when we go to the chapter of leaching in design. But here, for this course, having the knowledge that you have some basic equilibrium kinetic data. How fast is dissolved the elements, and even you can have solvent extraction test. We call it isotherms, equilibrium isotherms. And you can say we will have 10 equilibrium isotherm, 5 points. You can determine the chemical assays that you're going to need because you're going to charge. More importantly, you invest a lot of time in this because you are learning. Cost. You need to charge, so you give me for free. And a proposal, you have a cost estimate. So, sorry, by the way, the rest of the thing, the economical first estimation, that's fine. I mean, it's wrong because you don't have any kinetic data, but you end up with numbers saying, for example, this is the available material that we have, tons, a lot of tons. This is the market. You need to show that you can cover the market or even more in Germany. You already saw that. You have huge amount. You already know that. You know there are processes. You don't know the time. Leaching 1, 2 hours, 3 hours. It doesn't really matter for the size. So you can tune a little bit how much is the capex. The capex, you don't need to estimate the capex for everything. You estimate the capex for the more important equipment. That will be an agitator reactor. So this agitator reactor, you can estimate the capex. It will be 500,000 depending on the amount that you want to process. And then the rest of the equipment will be 3 times. The rest of the equipment. And the rest of the aspect of the plants, civil work is another 3 times. And that's it. So this is a $5 million project. It's an estimate. Because you need to demonstrate if it's possible. If it's too expensive, you demonstrate, you know what, it's really, really expensive. Extracting 1 part per billion of germanium in this is too expensive. You know, if it's 1 part per billion, probably going to be a lot more expensive. You can estimate that. Okay, cost estimate. You
Sorry,
did some. Sorry, go
the
ahead.
previous steps that we are going through the block diagram, we just named the process, but we didn't mention about the specific equipment
No.
and the flow sheet. We didn't
No,
use
yeah,
it.
just the block diagram. That is called basic engineering. You mentioned the operations. You need to solid liquid extraction. We'll come back to that when I'll show you a general process when we work with the tailings. We just finished a project with MATLAB to have multiple flow sheet and evaluation. You will see. Okay? This is block diagram. You have a general one. Yeah, to answer you. You will have repulping or producing the pulp. Mechanical liberation, if it's the case when you're doing this is mechanical liberation, repulping, this is one specific stage. And then we call it chemical liberation, which is leaching. It can be autoclave, atmospheric, alkaline, but you remove from the matrix solid and ion. Then you have selective extraction, and depending on the concentration, if it's very low, it will be ionic exchange, membrane. If it's pretty fair, the number, it's 5 grams per liter, 2 grams per liter, it would be to solvent extraction. Okay, that would be selective extraction. And then once you have concentrated your product, 30 grams per liter, 50 grams per liter, you can go either electrowinning, precipitation, crystallization, and in between, of course, you have purification stages. We will see the case today, the zinc case. Okay, zinc
It
case.
didn't provide flow sheet, right?
Sorry,
It didn't provide flow sheet.
you provide a block diagram.
I know that flow sheet.
Yeah, no, because you're showing equipment. You're showing equipment. This is part of engineering. Okay. And to finish this part, I don't want to be extended to that. Roughly, senior engineer can be from 100 to 200 an hour. These are the senior engineer. It doesn't mean that it works 4 or 5 hours per week. This is our case, 1, 3, because we're doing many things simultaneously. Okay, this is that one. For example, it's not recorded, but for the last project that I did with Escondida was about this amount. The guys who hired us for this amount. It was 120 hours. It's a lot of money in the project. They hired you for hours to be consultant. Okay, and then we move to engineers with experience. You can check it. It will depend on the operation, but easily $20, $50 an hour, and then you are going down to junior engineer. So the important thing is to have a rough number. The equivalent, because you are hired by number of hours, it is another. The last thing that I want to talk about that. This is a specialized consultant. I mean, just to have a number. A good consultant, it will cost you 500 US a day. Standard consultant, a day. Since you travel a day. A good consultant will be 1,000 a day. Okay. For the case of the rest of engineers, you need to. I have contract people 100, a professor for 500 Canada, and I have it. It's very clear per day. When I was student in a PhD student in Albion Shell, I received 500 Canadian dollar, which is 400 per day, since I fly from Montreal to Fort McMurray. This is something usual when you are international consultant. I'm talking about that. Okay, let's come back to the junior, which is your case. So you need to be fair. I'm fair with the students. So depending on number of, regardless the number of hours, okay, what is the salary in the market today for a junior engineer working in Chile? That will be about 2,000 a month working here. 2,000 US, but it's not that much. If you work in a mining company, that will be way more, 3, 4, plus bonus per year. Okay. So when you have this salary per month, you convert it into money per hour. You have 180. You understand? How to estimate the budget when you have a consultant 2 to 5 hours per week. It's reasonable because you ask for something specific. You ask to analyze data when a senior. The other guys are doing the experiment that will be a regular job. You must be very clear with the number of experiments, repetitions, and one of the things when we make a lot of mistakes when you do analysis. In analysis, which is not that expensive, but you need to have replicates all the time. The most important experiment, 3 replicates, because you want to have a very accurate kinetic. Never use a single dot. That's it. Okay? We will come back to that, but I think this is a very important message for you, understanding what is a proposal. The one that you give me is pretty much close to in between to a paper, which is good too. We also will go to a paper. Have a different structure. Now I want to move to show the case of zinc. The case of zinc. Sorry, go ahead.
How should we make a rough number for the equipment?
Okay. So now you need to have some calculation. As we mentioned in process design, it will be if it's a batch test and you want to process. Okay.
Let's say we have a size of the equipment and
No, you don't have the size. No. It's all okay. The only thing that you know, this is my raw material. This is the composition. Okay, so you can have, for example, 1,000 tons of germanium per year. Is how much do you have? And then on the other side, you need to have the demand. Okay, and the demand it will be 10 tons per year. I made up the number. So you can produce more than is available. Okay, and then you decide. I will cover 10% of the demand, 30% of the demand. Okay, all the way around. Tailings we have more than enough, millions of tons. These tailings can be used for roads, for concrete elements, and you say we have this amount of material and we need this amount for roads. Okay, it's all the way around. You have more material that can cover the roads. So you need to determine what fraction of the market that you cover. It can be 10, 5%. Now you know the size, how much material you're processing. You want to do this. No calculation, only data from internet. You're guessing things. Okay, 5%. That happened to us. Actually, still I have, if you want to be involved, I have one guy, investors that want to extract, I think it's niobium. Let me check in Bolivia. Because they have 30% niobium, I'm not quite sure. No, tantalum. Tantalum usually comes with your mineralogies. When you have tantalum, you also have there 2 elements when you have tantalum. Tantalum is being used as a material for very hot turbines. It resists a lot. Tantalum comes always with, well, anyway, so one investor came up because they own a property in Bolivia. They have pretty much stones with tantalum and something else. I'm not sure about that. And I did exactly like that, and I had the numbers. So they were about to hire me, so I review, because I'm technical, to use some of the processes to extract tantalum. Exactly the same thing. And to determine the market, we say 10% of the market, but in this particular case, China and Brazil, I think it's tantalum. I need to check tantalum. But it's something like China, Brazil, they produce a lot. So the market they had too much tantalum. Okay. Once you have the size, how many tons of material are you want to process per year? Now you need to put some efficiencies, and efficiency is very tricky. The more stages you have in your flow chip, so you don't have 98% recovery, because you have too many stages. So if best case scenario, you have, even when you filter, you lose some material. So each stage, it adds an efficiency, and you multiply the efficiencies. So you have 10 stages efficiency, 80% efficiency, you have very low conversion. Or 3 stages, you need to guess. 85, 95 is a very good process, probably leaching, but perhaps you require more time, so end up with 60. Okay, to make a rough number, just an estimate, you can have 30% or 50% efficiency to be conservative. Yes, to be conservative. Because you don't want to make a mistake with the main equipment. So you're producing that divided by 0.3, you need to put 3 times the feed in the feed material. If you want to produce 1, you need to put inside 3 because you have 30% efficiency. That will give you the size. And now, depending on the process, you pretty much know what is feasible to have as a leaching, 2 hours, 3 hours. 20 hours, never. It's a lost project. And we have in the proposal that I was talking about, there is one university proposing a chlorine leaching for concentrate with 120 hours. I can show you, but we cannot laugh at them. Or okay, you can laugh. Okay? You know, it's very simple. I'm old. I'm giving you all the tips, all the things, because I've been learning for 30 years. Okay? No more than this. No more than this. And then the amount of hour that you need, the amount of hour will be pretty much experimental. This is experimental design. Repeat test, testing, repeating test, analyze. Remember, X-ray diffraction and quantum is really, really expensive, by the way. You need to minimize that, but it's good to have it. It's good to have at least one to avoid having an over cost proposal. And then if the results are good in the preliminary test, the next stage is improve the sampling. Why is it important? You can check a Chilean company called Monument, because they want to extract critical elements from tailings. It was a mine in US. What happened with this company? I don't remember how much they lose. They invested, create the project, but they have the wrong sampling and they lose a lot, it's public, a lot of money because it didn't work the plant. Because the original characterization is really, really heterogeneous. It changed a lot. Especially tailings. We have characterized all the tailings, not all, but most of the tailings in Chile. But all of them are made 2 meters depth, and they assume that is homogeneous. And tailings is not homogeneous, definitely. We have another work on that. It's heterogeneous in particle size, it's heterogeneous in liberation, and also in element composition. So the most difficult thing for the final project will be always sampling. And when you study a copper mine, you're from mining. When you study you have a lot of samples and try to determine how much clay you have. It's huge distribution. So how are you going to this? You may mix. You have 10 deposits. You may mix in order to have something stable. That comes the planning, mining planning. But still, the uncertainty is really, really high. Okay, but you live with that. Okay, I'm talking about too much of process design. This is not part of the course. We're in sustainable. So this is an example. Clear? The work is good. We need to improve only the scaling up, but it wasn't a proposal. Okay, it was a proposal. But no worries, I'm playing and kidding all the time with you guys. It's better like that to learn. Okay, I'm gonna switch to another presentation. So I'm gonna stop this pause recording. Francisco Hernan, this is a byproduct generated in the steel making from iron scrap. It means you can put wasted cars, refrigerators, all the element that contains iron, not copper, iron. So crash cars, pipes, electrodomestic, refrigerators, kitchens, a huge pipe. And those are molten using an electrical arc like welding. And during this process, it generates a dust because you evaporate all the metals and then generate droplets of molten metal that contains valuable elements. So today for this company, this is 2018, so you need to update them. You need to update the cost. It's about $1 million per year, the disposal of this dust. So if you think in terms of business, you are paying to dispose a material that contains good elements. So when you are looking for a sustainable engineering, you need to look for those which are current problems. The idea is convert problems, you are paying for that, and convert that in something that you can extract something. You understand? It's meaningless trying to do an effort when you have very little amount, when you don't have a real cost. Okay? So this is Gerdau. So here is evaluate a business strategy. Actually, it's process design because we are presenting that for the investors. Yes. To reuse steel mill dust that is subject to the quantity. It contains zinc at the end. So what is the step that we need to know now when we're doing a project? Characterize the element. Then marketable products with zinc. What it can be converted? We need to have a study market. Zinc sulfate, zinc oxide, zinc element. And we haven't spoken anything about the process. We have this material and we have these options. In between, we have process engineers. No worries about that. We are good on that. What is the typical way that you start? Leaching reactor, solvent extraction. Understand? Okay. Then alternatives to convert, going from 1 to B, alternative. Second, experimental data to see if it's true, kinetic, precipitation. Once we have this data, process design. Remember, you already have here, Zara, here, you have block diagrams. Process design is converting this block diagram in an actual equipment. It will be a batch reactor, continuous reactor, okay? And then once you have the sizes, because here you decide the size of the market, once you have the size, yes, you can have the economical evaluation. You see? Simple, very simple. So, this is the many smelters. Yeah, good idea. We can visit that too because it's here in. Then you have a wet scrubber when you precipitate and condense all the material, capture the dust and generate the the dust here. And here you produce steel bars for construction. This is the main use. Steel bars for construction. Gerdau is really big, isn't it? It's really big company, really big. I think they are responsible for 40% of the iron production in Chile, something like that. This is yes, I want to see this like a Star Wars. It's fascinating to see the electrical arc. It's very scary. I mean, have you seen something like that? It's more scary than a smelter, having an electrical arc. I think it's 10 megawatts, if I'm not mistaken. In order to see what happened or what are the more prioritized reactions, you know what I mean? The prioritized reaction, you need to go to an Ellingham diagram. You do it in HAC. Actually, this was in HSC, the one that you have. Or we have a license to. We have 2 or 3 computers with HAC. That determines what are the more favorable reactions. You don't remember that or you don't know, please study that, but it will show you the thermodynamics of the reaction, the priority, what reaction is showing up. So we're producing zinc oxide at the end, at these conditions. At this temperature, we're producing zinc oxide. You see? This is a prediction, what is happening. Thermodynamics, it doesn't show you the time. Thermodynamic is the tendency. Where are we going? Not how fast. Okay. Yes?
So with the Eisenhower diagram, for this case, the interest was
Just to say, the most likely product that we will have under this condition is zinc oxide. In theory. Now we need some data, production data. So this is the tons dust that you are producing. And then, of course, what we need? Zinc. So you see the zinc content is quite high, 40% zinc. It's a lot in a dust. From the point of view of leaching, it's great having dust with zinc because it's fully liberated. You know what I'm trying to say? Fully liberated. But of course, if we want to leach, we'll have a restriction with the mixing. You already know that. So you see, data from the plant. What is that? Rudolf, explain why we need to do that. To know the species. And actually we were right. So this fingerprint, you already learned that in Oulu, from the guys who are listening. This is it's called X-ray diffraction. It means you have an X-ray changing the degree of incidence, and it will give you a fingerprint of specific mineral elements. In analogy, Francisco, if you're listening, Francisco and Hernan,
Okay.
in analogy, perhaps you already know. Do you know something before of X-ray diffraction? Hernan or Francisco, X-ray diffraction? Hernan?
Sorry, can you repeat?
X-ray diffraction, do you know how it works?
No, I don't.
Francisco, what about you?
No.
Okay, in short, you can have first fluorescence X-ray to determine a specific element. That will be fluorescence, XRF. But in this case, we have XRD. D stands for diffraction. You are changing the angle of incidence, XRD. And that can show you the fingerprint of a specific element. If you have sulfate, you have a different shape of this curve. Here is the angle of incidence. Okay. In the same way, when you have FTIR, you know FTIR. It was mentioned yesterday. Professor Tania Sandoval, student. FTIR, fast Fourier transform infrared. In the same thing, you have different angle of incidence of an infrared. Sorry, in this case you have frequencies, and you have resonance, and you have exactly the same response, but for organic element, and you will find functional groups. So they were fixing elements. You remember yesterday the presentation, fixing elements, and they want to determine if this element is present. To do that, you use a different technique called FTIR. That is very good for us when we want to characterize frothers. Frothers are a mix of things, and you want to be sure that you have the component, use FTIR. Okay, so this allows us to determine the mineral composition. That was good because it talks with the previous theory with enneagram diagram. Okay, I want to speed up a little bit here because you have the presentation. So, Sarah, these are possible routes. We call it in chemical engineering, we call it routes, possible routes Okay, that's pyrometallurgy. I'm pretty sure that I can translate that, but hydrometallurgy. Do you have the Spanish or English version? English. Yeah, sorry about that. I have the, yes. I'm pretty sure that I translated. I update that. Anyway, and you can you send it back this one to me to be sure that I have it? Not now, but can you send it to me the presentation which is translated? Well, anyway, so those are routes showing different, you see, block diagrams, possible, and these routes are related with the possible products. What is the next step? Knowing the price and import in the case of Chile. We want to have the Chilean market. We need to have both production, tons per year, and also price. Okay, this is zinc oxide. It's 2000. Then you have, sorry, I didn't get that. This is marketable potential products. This is export, import and export. If we export or not the material, and this is for zinc sulfate, more volume. This is import, so that's good. We're importing. Export very little, very specialized condition, very little export. That will give us the volume. Again, if you have 1 million tons of zinc and the market is 1,000, you see, you have far too much. And this is good because you can have very low price, you can compete. You can have as a strategy 100% of the market, for example. Okay, so zinc chloride and so on, all of them were done. You need to cover these numbers. No import. Metallic zinc, same thing. And then this is important for us. Evaluation. This is where your creativity is. First, you need to have data. Product, possible product, you already know they are possible product. There is not to make something trioxide magnetic zinc because we don't have it in the product, in the matrix. We have the elements. You have how much are marketable. Perhaps you don't have data in some of them. Extraction route, the most important parameter, just to understand the process route. Roasting, discard. Roasting is complex. We want avoid by all means roasting, smelter. We want to avoid that. Leaching. Okay, we know it's leaching. Process recovery. You already know you remember the data that I gave you. So this stage only has 60%. So you want to have a conservative number. You put 30% in the whole process because one of the stages is already 60. Okay. And you have in all your proposals how much? 90, 95, 98. But you learn, okay? Potential volume, that will give you the size, pretty much the same. So whatever now is around here.
This process recovery should the final recovery of this.
No, it's only leaching. Or I'm sorry, I'm not sure. I need to review in the document itself because they are referenced there. I mean, we have a written document. I can send it. You need to go to Google Translate to have it in English, but I'm not sure. Huh? Okay, then processing technologies. Once you have decided leaching, what happened after? You already know that. Solvent extraction, electrowinning, metallic zinc, cementation is like precipitation, yes, crystallization, zinc sulfate. Okay, why we decide zinc sulfate? Because it's good for agriculture. Okay, you improve growth. Actually, it can be written all the way around. You have zinc, you have a more healthy. Yeah, if you don't put zinc, you have non-healthy leaves, and you have zinc, you have more crops. You increase the efficiency. So you are paying for a product to produce more. That's the thing that you are doing. Okay. Experiment. Very simple experiment. This is called bench scale. In a bench scale, the size of the equipment, it can be even 50 milliliters, 20 milliliters. when we work with the cesium extraction, we have very little extractant for resin. It was, I think, 20. But then you need to know what is the possible concentration that you have there, because if you have part per billion, you need to have capabilities to analyze part per billion. You need to have a guess of the concentration. So the size of the equipment and the amount that you have will depend on the analytical technique that you have. If you have atomic absorption and you want to have repeat test, and if you want to have a kinetic data, you are extracting in time, perhaps you're going to need 5 liters, 2 liters, because you are extracting 10 cubic centimeters a sample in time to be analyzed and get the kinetic in a single tank. You don't need to run different tanks. You need to think the size depending on what you want to do. And this is connected with the analytical technique. You have 1 liter and you are extracting 5 points of 10 centimeters, will be 50 centimeters. It doesn't change that much the volume of the reactor. In some cases, we don't have more option. That was the case when we work with iodine. We have very little amount, and we extract some solution to analyze the iodine in time, and we reduce the volume of the reactor. So when we calculate the kinetic, we have, of course, a kinetic removing iodine, but also changing in volume. So we need to correct the change in volume of the reactor. Will have different reagents. You know what I mean? It can be done. It's tricky, but it can be done. It's going to be always better if you have a larger unit and you extract very little amount in order to have samples. 5 points is fine. 3 is not good. One of the students in the Erasmus thesis, they have kinetic data with 3 points. This is not good. 5 points is the minimum. Okay? Got it? Agitated reactor, careful with the materials. Jade worked with chlorine and sulfuric acid, and she broke all the impellers. But we knew, because we're testing for first time the impact of mixing something completely different elements that change the ORP a lot. And you review the literature, you saw the presentation. There is no paper that explains how the ORP, the oxidizing potential change, and she demonstrates that generate chlorine. This is very unique. Okay. Then we have the kinetic extraction. Here is trying to demonstrate 2 effects: the temperature. Temperature always. This is for chemical engineer guys. Temperature in chemical reactions and leaching, whatever chemical reaction you have, you don't know it, you should know it right now. Let's keep it simple. When you have extraction time, it will be maximum extraction infinite, that depends on liberation. You already know that. If a first order kinetic data, it will be something like that. But this K value, I'm talking about Arrhenius. I want to just to show the guys there. I want to increase the size here. Okay, can you see now the blackboard now, guys? Okay, I'm talking about here. Can you see, Hernan?
Yes.
Okay, can you see here? Okay, we're talking about here first order, but this K value is function of temperature, okay, 0, and then you have another exponential data minus delta. The activation energy is an experimental data divided by R, gas constant, R from thermodynamics, P. So the kinetic is function of temperature. That's the reason that always we change temperature. Okay, we work with that. Muki, you work with that. Yes? Isn't it true that we did a lot of experiments to remove energite with different temperature, and we modeled this equation? Okay. It's important to know that. That was the reason. This is called Arrhenius equation. Arrhenius equation.
Yes, It is the extraction here, no?
So
Yeah.
this K value that you get from a specific experiment with specific temperature, you can relate the temperature different conditions with the Arrhenius equation. That's the reason you need to do 2 or 3 temperatures. Okay? Arrhenius equation. Okay, we'll come back. Now we are back to the presentation. So then you have here the impact of maximum extraction to a given time. They don't say the time. He studied 2 things here, seeing the effect of temperature and seeing the effect of volumetric content of solid in a given time. I don't really recall why it must be in a specific time. Iron extraction, why we are interested in another element? Because you are removing from solid phase to liquid phase zinc, but also you are adding other elements. And you know what? Iron is really, really, really nasty. It's difficult to separate. It can be converted in something that called jarosite. Rudolf, is that right? Jarosite sound for you? A component, jarosite.
Jarosite.
Yes.
Okay, I heard of it.
You remember? Okay. Tell something about that. You are our mineralogist. Okay, if it doesn't remember, not important, but it's really, really bad because it generates it's kind of hydroxide gel and it's difficult to separate in solution. In a different project, not from this, in a project where we work with zinc concentrate, working in autoclave, the most difficult thing to do is separate iron. So we have a specific paper on how to remove iron. Iron is a bad thing. So we need to see how fast it's dissolved because it will add contaminants, as well as cadmium and lead. And because imagine that you have many hours leaching, you will end up in your soup with a lot of lead, with a lot of cadmium, which is going to be difficult to separate further on. Remember, I have another. It will be your job. Find another paper with jarosite and talk about that. I think it's Fuentes. It's zinc, concentrate zinc. Fuentes, myself, Leiva. It's all precipitant zinc, something like that. You don't need to look for that now. Okay, so that's the reason because we need the kinetic of other elements, but it's not a different kinetic. You extract a solution and you analyze more elements. Same sample, you analyze more elements. Cadmium, same thing. Well, I'm interested because it will go to the solution. Cadmium, lead, same thing. By the way, we did experiment with our own resources. Just not put any money. And now Matias, it's general manager, suspect to collaborate more because we pay for that, for all this analysis. And now we're talking, this is kinetic. Okay, guys, you have 30 seconds to determine the parameters, 20 seconds to determine the parameters of the kinetic test that we have here. Sorry, by the way, remember, always put dots for experiment and replicates, never lines, no lines, this is wrong. And when you put the model, please do not do it like that. Put more time, more data, because you know the model. And never use point, just the line, segmented line, okay? Experiment dots, and this, you don't need to use the same table. You need to have a different table with more continuous number, preferentially a geometric progression, okay? Well, we will come back to fitting data. Anyway, you have 20 seconds to determine the parameters. You know that. E, it will be something like 55, I think. K, hard, because we are using the 63.2% maximum It's kind of hard. It will be 5. Give me 5 minutes. 1 over 5 minutes. Give to you 1 over 5 minutes. Okay. How did I did it? Look. From 0 to 55 times 0.632. Make a simple 0.6. It will be 30. So when you have 30% recovery, more or less, when you have 30% recovery times it's equal to 1 over k. Remember, you have this number here, minus 1. Minus 1. And when you have there, go here, this is 10, that will be 5. So k is 1 over 5. Got it? Easy? Yeah. When we came up with this formula, if you see here, this formula, when the value of t, the time, is equal to 1 over k, that becomes minus 1. And if you calculate 1 minus exponential of minus 1, it will give you 0.632723. 0.63% of the response. So when we have this condition, this value will be 63%. So we need to look when we reach 63.2% of the maximum conversion. That's the thing that we do. So here we have about 55, multiply 55 times 0.632. I just estimate. It give you 34. Okay, so here is 30. Look, no, here is 30. 34 could be something little around here. So in this extraction, it has passed the time, which is equivalent to 1 over k. So I need to read the time here. It will be 3 minutes. Sorry, I was mistaken. Fascinating. If you take the points, you take these points. Actually, this is exercise that you wanna train. You see the data, and even you know the size. Okay, 3 minutes, 4 minutes. I see it like that. 3-4 minute reactor is a very fast chemical reaction. Listen up while you're learning. Just showing the plot, showing the data. You already know the kinetics. Yes.
How about maybe we drain a tangent to the curve of the
Sorry.
drain a tangent to the curve?
So what? Sorry. Here. This is the maximum only. Yes. You do that to get the maximum. But I mean, roughly it's 54, 55. Or you mean here, the tangential? No, no meaning. No meaning. No meaning. No. Okay, but that comes from this analysis, saying the K. Okay, you got that? And now this is experimental validation. Experimental validation. Actually, those experiments were conducted here, so they have different stages of solution. Remember that this is the process design. I think you have it here. Cementation, crystallization. Yeah. When cementation is when you, for example, you have copper and you add iron, it will replace the iron. This is cementation. Okay. These are the actual product that we finished here. And now more detail of this will be another basic engineering because it's block diagram. I'm not saying what type of filtration, I'm not saying what type of crystallizer was filtering. In this case was lab filtration, washing, drying. You need to watch, remember in filtration you need to watch the cake and you lose material. So each stage add inefficiencies. Okay. Those are actually, you ask that to remove the contaminant, which is lead and calcium here, and there's something with cadmium. And once you have that, now you have the process design. Process design will tell you what type of equipment. That will be an agitated tank. You need pumps to move things in between, and then you can have a more accurate estimate of capex. But really, at this stage, in a proposal, it's not really important. You say you have 3 leaching reactors, and the rest of the thing, this is 30% of the investment, because you need pipes, you need piping, and those numbers I didn't make up. If you review chemical engineering handbook, you have a table when you determine the percentage of civil work. For example, you have a big plant, process control, whatever thing you do, it will be 30% of the investment. Okay, because they're practical. Construction, in the case of pharmaceuticals, it's 5 times more expensive than traditional, because it requires some specific, for example. But those things, I think you saw it in the process design. Okay, now the size of the equipment. We need to make in this case, it's batch the equipment, so the kinetic is the same. We just scale up the impeller with tip speed. Okay, we already know the market, the price, $1.5 per kilogram. Investment, because you know the tank and all these calculations that I say earlier, 3 times for the equipment, 3 times for the rest, something like that. Perhaps in this project they have more detail of the economical evaluation, but depends on how much time are you investing on that. Okay. Very important, when you do the economical evaluation and calculate the net present value, common mistake, the discount rate. Common mistake, very common mistake. And the evaluation period. Sometimes students, when they see that the economical evaluation is not good, they evaluate in 30 years, 40 years. This is completely wrong. It will depend on the project. There are projects that they want a payback in 2-3 months because you're doing a consultancy. Or reverse osmosis is 30-year project. In general, 1-2 years is expected for an investor when you need to put equipments. When you need to install equipment, 1-2 years is expected to have the payback period. Okay. When you have a change in operating condition, adding sensors, something like that, we're expecting 3-4 months. It can be done. Okay. Otherwise, it will not be a winner project. I'm not sure if you are familiar. If not, you need to be NP value. Net present value is a formula when you have a cash flow in time. Okay, if you need to review that NP value, and you put in present value all the money, because in 10 years more the money will be different. Very important, in this formula you put a discount rate. Common mistake. This value, in general, it will be 12% for a regular project. For innovation project, it will be 30-40%. Because this value is saying, okay, I can invest in your project or I can put the money in the bank. So it's a discount rate. It's a ratio that you want to compare where the investor is going to put the money. At this moment, the only thing that I want you to know, when you put this value for innovative projects, something that is completely new, you put 30%. When you have social projects, when you have money from the government, 8% is a good number. In Chile, or in general, mining projects are evaluated with 10%. Huge investment and something well known. That's the reason, because they are resilient to put too much new equipment. Okay, 10%. Okay, if you don't know that, it will be your job. Study a little bit more. The guys from chemical engineers, I'm pretty sure they know. Okay, remember, don't make mistake with the number of years. This is related with the real project and the discount rate, which is in the formula. That will give you the total project actual value of the project. You put money and you're going to return certain amount. Okay, it's on a spreadsheet. It's not that big, not more complex than this. This is exactly the cash flow rate. At the beginning, you are losing money, and this payback was 3 years. The payback. That is a good number. This is when you have 0 band, 56, but it doesn't show. Okay, you want to complain here. After 5-6 years, you didn't put the discount rate, because we talk about a lot that. Okay, so in this project, so that you invest. Sorry, the investment. It didn't say the investment. I don't see the investment. Yes, $3.6 million. $3.6 million investment, and you recover the money in 3 years. Recover the money, and after that you're utilities. You're getting money back. So we don't reduce 100%. We have still this. We need to dispose, but we dispose without, because we separate. You have this amount. This is an important message. You have this amount with lead cadmium, toxic waste. Okay, but if you reduce the material and remove cadmium and lead, it's different category. It's not that costly. You know what I mean? And if you are able to remove and concentrate cadmium and lead in very little amount, it's going to be less expensive because you are treating less volume. Okay, you understand that? So you need to analyze from this point of view, and that's it. That's it. I don't see the discount rate. After that, you use a sensitivity. I always confuse sensitivity or sensibility. Sensitivity analysis. You take the project and you change. Usually, you change. You play with the price. 1, 2, 3. Different scenarios. You play with the investment, for example. And also you can play with the recovery if you want. But usually you have at the end of the pipe, which will be the price, or at the beginning, electrical cost, if it's the case. Just play with those numbers in order to have a cloud of possible scenarios. Okay. Remember, at this stage, we have 50% error. Remember, I show you from 50% error. So we don't expect 0, 0, 0 is too much. 3.6 million. That's it. We don't need decimals here. Okay, so real case, the person who did that already is the general manager or EcoASA, and he worked with that. Planning to do this project. Part of this stuff we did it with Jay, because we work with lithium battery recycling, but we don't have a lot of dust of batteries, so we play with this dust like a proxy material to study leaching. Okay, that's it. We will continue with study cases in order to be more expedite. I already updated PowerPoint. I will send it to you, so it will be your job. Review it, then we'll review it here, but you already know that we are talking about. Okay, that's it. Simple. So if I ask you, can you create a project as a group here in 3 weeks? Proposal for extraction of neodymium of flue dust. Can you make it? Can you make it? Can you estimate cost? And after that, can you propose an experimental design? Steps? See? Can you do the experiments? Yeah, we need to play with that. Okay, that's it. Francisco,
Yeah,
are you clear with the? You didn't participate in the project with the student, or no?
not
Did you
yet.
work? Sorry?
Aún no, profesor.
Okay. So you are missing one project. Okay, we can fix that. So I think we can talk afternoon, or send me an email to make your follow-up in order to have a better use of the course. I mean, the idea is you interact with the students, okay? Francisco,
Yeah, bueno,
the way you learn is doing things. You know that. This is Santa Maria style. Okay, so we are finishing that now here and continue in Graciela Muñoz room. Sorry, I forgot to show you a lot of. I have a lot of toys. I will be in the next. Okay, just to finish up about that, I received this in US in Las Vegas. It was a compostable plastic bag. Some students were presenting that, but I said, okay, this is a possible solution. But what is the best solution? Avoid using plastic bags. Avoid using plastic bags. So everybody was saying like that. Well, in Chile that was banned in 2018. No plastic bags. And I was with my daughter yesterday, so she sent you some mandarins, how do you call it? It's not for you. You want. Well, for you. Okay, Francisco. See you in one block more. Okay.
Okay.
Okay. So this is compostable, but who cares? This is a 8-month project, more or less, but it has a lot of TAs to make this project. Pretty much same with Jay. I hired to Jay three technicians, because we have a campus with engineering, and in Viña del Mar we have a campus with technician, metallurgical technician, chemical technician.